Okay, so today our mathematician spotlight is Professor Mavinga of Swarthmore College. Associate Professor Mavinga. This is breaking news. So we just got an email on Saturday saying that Professor Mavinga had been promoted to Associate Professor and thus tenured. She studies nonlinear differential equations, like some of the people that we've talked about. Since you guys are consumers of academia, I just wanted to tell you how these things work. So Professor Mavinga is now an associate professor. Before that, she was an assistant professor. So when you're hired into tenure track, new professor, you're an assistant professor. That means you're not tenured. At Swarthmore, after 3 years of being an assistant professor, you can get your contract renewed for another 3 years. So Professor Baranka, for example, of the math department, just got his contract renewed. He gets another 3. After that second time, then you've had 6 years here. Then you come up for tenure. You make a whole portfolio saying how you're so great. And then they look at it, the department and also the college looks at it, and they maybe decide to give you tenure. So there's 6 years between you when you get hired as a tenure track assistant professor and when you get tenure. After that, after about another 6 years, you can get promoted to full professor, which doesn't change much except you get more money. And then after that, you could get a named professorship. So some people have given money, and so you might find some, like my advisor at Brown, he's the Chancellor's Professor of Mathematics. So that's one level above. Below these, there are people that are not tenure track. So for example, visiting assistant professor. So that's what I am. I have a 3-year contract here. This is my first of 3 years. And at the end of my 3-year contract, if I haven't gotten another job, I won't have a job. And below this, so I have actually a quite nice contract. It's 3 years. I have it's a really good job. But below this, there are people who are adjuncts, probably not at Swarthmore, but these are people who just get paid to teach each class. So for example, if I were teaching you as an adjunct, maybe Swarthmore would give me like $6,000 to teach this class for the semester. That's it. So that's what an adjunct is. I don't think Swarthmore has any of these. We all have pretty good contracts like this. So Professor Mavinga has tenure now. So when people think about tenure, they think it means like you can't be fired, which is basically what is the case. And the reason this was invented, tenure was invented, was for academic freedom. So there's not so much controversial stuff in math, although I can say controversial things like, sure, I can say controversial things. My research probably isn't too controversial, but there are areas of research that are controversial, like stem cells, for example, are controversial, things like that. So the reason that people get tenure is so that you can't be fired, so that you can do controversial research that moves humanity forward, but you can't be fired for it. So that's the purpose of tenure. You can lose your job as a tenured professor, but it is very hard to do. So now that Professor Mavinga is tenured, in order for her to lose her job, everyone with lower status has to lose their job first. So the only way that she could lose her job is, for example, if Swarthmore went bankrupt and did not have enough money to meet its payroll. They would have to let go everyone, like all the staff people and all the visiting professors and everything before they let her go. So it's very, very good job security. Yeah?
What if after you get tenured, you start slacking as a professor, and then you're just not as good anymore, and you don't care about your job?
Yeah, right.
You not get fired from that.
If after you get tenure you start slacking off on your job, it's very hard to do anything about it. It really is. So for example, not here, but I know some places where there are people who have been professors at the place for 40 years who are still an associate professor. And that's pretty bad, because it's not too hard to move from associate to full professor. You just have to do a little bit of research or something. So it means that they just stopped working and just didn't care after that. And it's too bad, yeah.
If you want to work somewhere else, do you start at the bottom again, or do you also get tenured another?
If you want to work somewhere else, you probably negotiate to get hired with tenure. If you've just gotten tenure somewhere and then you try to move somewhere else, it might be sort of chancy. They might say, oh, we're not sure, we have to hire you tenure track, we'll give you a short tenure clock. You might have to go through the whole process again. But generally, once you have tenure and you try to move, you want to get hired somewhere with tenure. Because it's like a golden ticket. Why would you give that up, right? Yeah. Yeah. So I am going to be on the job market every year trying to find a tenure track job. But in the meantime, I have this amazing job, which is really wonderful. So life is good. Okay. Oops. Okay. So, last time we talked about math, we were outside. And we were talking about Lagrange multipliers, so optimizing a function under a constraint. So today, we're just going to play with Lagrange multipliers and use them to solve our problems. So, the first thing we'll talk about is an application to economics. So how many of you have taken an economics class or studied a bit of economics? Yeah, most of you, yeah? A lot of you. So in economics, you want to maximize total utility, whatever that means. So for us today, we're going to call that happiness. You want to maximize your happiness. And you have some indifference curves along these curves, you would have the same amount of utility. And then you have a constraint, the amount of money, for example, that you're able to spend getting goods. And you want to maximize your utility under your constraint. So we're going to use Lagrange multipliers to do that today. So suppose you get happiness, which is your utility, from pints of ice cream and ice cream cones. So the cone in this case is just the dry bit, like the cone, with no ice cream inside. According to happiness as a function of pints and cones is square root of the number of cones plus 3 times square root of the number of pints. Okay, so square root function is usually used for utility because it is how things tend to work. So, for example, it's because it's always going up, because always getting more stuff makes you happier, but the slope is decreasing. Because, for instance, if you go, all of you, I think, have no pints of ice cream right now. Is that right? No pints. And if you were to give you 1 pint, you'd go from 0 to 1 pints. It would make you a lot happier. Agree? No? Well, for many of you, you would get happier if I gave you 1 pint. However, suppose you all came in here with 100 pints of ice cream, like already in your bag, and then I gave you an additional pint. You would not be that much happier. So going from here to here, your happiness increases a lot, but going from like here to here, your happiness doesn't increase so much. So that's why it's a square root function. Also, I'm assuming that getting an additional pint would make you happier than getting an additional cone. So maybe 3 times as happy. Something, or, well, times square root. So anyway, getting additional pints makes you more happy than getting additional cones. So that's why this is plausible. But it's a big question in economics, how exactly to write down a utility function, because you don't know what people's happiness actually is. So there we go. And our constraint is you have $20 to spend on pints and cones. That's it. So how many pints and cones should you buy? To maximize happiness. This is our question. So if we draw a picture, the curves of this form, square root of c plus 3 times square root of p, if we put pints down here and cones up here, they look something like this. Okay. Oops. And they shouldn't cross, and they hit the axes. And then, so these are level curves of happiness equal to a constant. So some level of happiness. And then you have our constraint. So our constraint is that we have $20 to spend, and we're going to get pints and cones. And pints cost $5. I didn't say that. And cones cost $1. So pints cost $5, and cones cost $1. which is about what they really are. About. So you're going to spend it on pints and cones, $5 for each pint, $1 for each cone. How many should you get? So our constraint looks something like this. And there could be other constraints. Maybe you have $20, but maybe your friend has over here only $10. And then your other friend has $40 to spend on pints and cones. And so these are constraints of the form 5p plus 1c equals a constant. And you can see, we know that happiness is maximized. Well, if these curves make you more happy as you go out, and so you'd want to be on the furthest out curve that you could get. So you'd want to get on the place where these are tangent. So this is our goal, is to find this point where our utility function is tangent to our constraint. That's the goal. So let's do it. So we want to maximize happiness as a function of pints and cones, which is square root of c plus 3 square root of p, subject to our budget constraint, which is g of pc, which is c plus 5p equals 20. We have $20 to spend. Okay, so let's do it. Okay, so Lagrange multipliers. Equation says that the gradient of f is lambda times the gradient of g. So just to remind you why this is the case, this should be h. We called it happiness. So the gradient of h is always going to be perpendicular to the h curves. So the h curves here are the blue curves. So maybe the h curves, let's see, it's perpendicular to the curve and points in the direction of increase. So at this point, for example, the gradient would be pointing that direction. So along this curve, it's always pointing that direction. And then the constraints are the form 5p plus 1c equals k. These guys are also perpendicular to the pink curves and pointing the direction of increase, which is again to the right. So the perpendiculars to the pink curves are also like that. And at a point where these are tangent, the blue curve, the blue vector and the pink vector point in the same direction. So essentially, the gradient of g equals gradient of h, because they're in the same direction. But they might not be the same length. One of them might be shorter than the other. So the gradient of h equals lambda times the gradient of g, possibly multiplied by a constant. And we call that constant lambda, which is Greek letter L, that stands for Lagrange. So that's where that equation comes from. And now let's use it. So the gradient of h, let's write down the gradient of h. So derivative with respect to c, let's see. Let me write this in an easier form. This is c to the 1/2 plus 3p to the 1/2. That makes it easier for me to take the derivative. So the derivative of this thing with respect to c is 1/2 c to the negative 1/2. And the derivative of this thing with respect to p, well, 1/2 times 3 is 3/2. So 3/2 p to the negative 1/2. And that's equal to lambda times the gradient of g. Let's do the gradient of g. The derivative with respect to c is 1. And with respect to p is 5. Okay, so that's the Lagrange multipliers part. And now this gives us two equations. The first equation is from the first line. So 1/2 c to the negative 1/2 equals lambda times 1. And 3/2 p to the negative 1/2 equals lambda times 5. Okay. So now what we want to do is figure out the relationship between c and p that will give us a maximizer. So you can solve this however you want. But the standard thing is to eliminate lambda, because we actually don't care what lambda is. So sometimes solve for lambda. Here it's very easy to solve for lambda. Lambda is 1/2 c to the negative 1/2. So we can plug that into the second equation, and we get 3/2 p to the negative 1/2 equals lambda, which is 1/2 c to the negative 1/2 times 5. Okay, so this gives us a relationship between P and C. Now let's just make it easier to look at. So maybe multiply everything by 2. We get 3p to the negative 1/2 equals 5c to the negative 1/2. It's hard to think about negative 1/2 power. So let's write this as 3 over square root of p equals 5 over square root of c, because that's just writing out what this means. And then maybe cross multiply 3 square root of c equals 5 square root of p. And now square both sides. Everything's positive, so we don't have to worry about losing solutions. 9c equals 25p. Okay, so this tells you that no matter how much money that you have, you always want your p and c, let's solve, c equals 25 over 9p. So no matter how much money you have, you always want to get 25 over 9 times as many cones as pints. So 25 over 9, let's see, 27 over 9 would be 3. So this is about 3p. So you want to have about 3 times as many cones as pints. Seem reasonable? Have a pint of ice cream, you can make it into 3 cones? Yeah, okay. So this tells you that over here on this picture are places where these curves are tangent are going to happen when c is 25 over 9p, or about 3p. So it's on the line, approximately the line c equals 3p, which is like y equals 3x, sort of this line through the origin. So that's where our maximizers are going to happen. So no matter how much money you have, no matter if it's you with $20, your friend with 10, your friend with 40, you want to have that many. So now we just plug it back into our constraint, the amount of money we actually have, to figure out how many pints and cones we should buy. So a relation from Lagrange multipliers is that c equals 25 over 9 times p. And now plug it into our budget constraint, which is that c plus 5p equals $20. And now we know c is 25 over 9 times p, so 25 over 9 times p plus 5p equals 20. Just combine the p's, divide by the coefficient, and we'll get p equals 18 over 7, which is about 2.6 pints. And then if you plug this back into your constraint, I mean either one, you could plug it into either one, you would get c equals 50 over 7, which is about 7.1 cones. So in real life, you probably couldn't walk up to the store and say, I would like 2.6 pints of ice cream, please. But if you could, it would be ideal. You would be optimally happy. Yeah, maybe you could get 9 friends and then get 26 pints and 71 cones and be happy. Yeah, questions or ideas? Yeah.
Exactly what's the Lagrange multiplier? Use the symbol lambda. Does it have anything to do with eigenvalues, right?
Right, yeah, this lambda doesn't have anything. Oh, does this lambda have anything to do with eigenvalues? So I'm pretty sure that the reason lambda is used is because of the Lagrange. But it's the same idea as eigenvalues, actually. Because an eigenvalue says if you take your vector and you hit it with this matrix, you get a multiple of the same vector. So 2 vectors that are multiples of each other. And this is also 2 vectors that are multiples of each other. So it's kind of the same idea, except we aren't hitting it with a matrix. Yeah, good question. Okay, the only thing you might wonder is you might wonder if maybe this is not a maximizer, it's actually a minimizer. Maybe this is the least amount happy that you could be. So we should check that this is a max, not a min. So to do that, just plug it into your happiness equation. So happiness of 2.6 pints, comma 7.1 cones. If you plug this in, square root of 2.6 plus, square root of 7.1 plus 3 times square root of 2.6 you get you approximately 7.5. Happiness is whatever units we have on happiness. And now you have to find a point that's close to this on your constraint. So some other amount of pints and cones that you could buy with $20. So if you look at this, you can see if you bought 2 pints, that would cost $10, and then you could buy 10 cones. So a nearby point on your constraint, so a nearby thing that you could buy would be 2 pints and 10 cones. And if you plug this in, square root of 10 plus 3 times square root of 2, you get 7.4 happiness. So this says that this actually indeed wasn't a min, it was indeed a max, which is what we wanted. Yeah. Yeah.
I get how on a function like this, where it's a nice even curve, you're letting sometimes like have to close and know that it's either min or max.
Yeah.
But if we have more complex functions, how do you know that we're close enough that we're really dealing with that specific point and not something that's happening far away?
Yeah, that's a good question. You might be concerned that this point is too far away to actually test whether it's a minimum or maximum. So you would probably be a good idea to try a point that's closer. But since we only have one solution, it means it's a global min or a global max. So it should be higher than everything else because we only got one point as our solution. So it's either a global max or it's a global min. So we can just check any other point. Yeah.
What if out of this we got that it's a global min? Does that mean that this function is just like not maximizable, which means that we really can't maximize it?
Yeah, if we had, suppose we had found out that this was a min, like this had come up to 7.5 and this had come up to 7.6 or something like that. Well, then we'd have to do something else. So we couldn't use Lagrange multipliers to solve this. So I think the thing to do would be to try the endpoints. So if you spend all your money, on cones, then you get 20 cones. So the happiness of 0 pints and 20 cones is square root of 20, which is something. And then if you spend all your money on pints, you would get 4 pints. So happiness of 4 pints and 0 cones is 3 times square root of 4. That one I can actually do. That's 6. Square root of 20. Is anybody willing to do it? What?
2 root 5.
2 root 5. So it's 4.472. Okay, so it tells you that spending all your money on cones would be the minimum.
But you can get pretty close to maximum happiness if you spend it all on pints.
You can get pretty close to maximum happiness if you spend it all on pints. Yeah. And in fact, if you walked into the store and you bought something you could actually buy, which is 2 pints and 10 cones, you'd be pretty close to maximum happiness. So it's not so bad that we had fractions. Yeah. So yeah, if you find this was a min, then you can't use Lagrange multipliers to find the max. You'd have to just check the edges. That's probably where the max would occur. Okay. Good question. So now you can maximize your happiness. So good that you came today. Okay. So now we will do something close to my heart, which is finding optimizing silos. So I got really obsessed with these questions about silos last year when I was teaching multivariable calculus and also living in a place where there were lots of farms. So I was living in Williamstown, Massachusetts. There are lots of farms. Anytime you see a farm, you have a silo. So here's our question. So suppose you want to build a silo. Silos are places where farmers store grain. So during the harvest season in the fall, you harvest all your grain, but then you have to feed your animals all year. So you have to store it somehow. And the way that they store it is in a silo. And silos look something like this. They are cylinders, usually with a sort of a hemispherical top. So that's what it looks like. And it's a very big thing. It's maybe about as tall as a barn or a house. So our goal is to, we have 600 pi square feet of siding, aluminum siding, to construct the sides, so this round cylinder part, and top of the silo. What dimensions? So the dimensions that we'd have to work with here are probably the radius and the height. Maximize the amount of volume of the thing. So after this, we will consider if we're allowed to put stuff in the hemispherical top as well. But for the time being, let's assume that we're just going to put stuff in the cylinder part. So volume of the cylinder part. That's the goal. So we have all this siding sitting around. We want to make a silo to put in the maximum amount of silage. Oh, and by the way, we already have like a concrete platform sitting here, so we don't have to worry about the bottom. Just that part. So let's write this down. We wish to maximize f of RH equals something under the constraint G of RH equals something. Okay. Whew. So we wish to maximize. Can you say what we would be maximizing?
Volume under a constraint surface area.
Yeah. So we want to maximize the volume of the cylinder part. So can you write the volume of the cylinder part in terms of R and H? 2 pi RH. Yeah. 2 pi RH, because it's the area of the base, which is the area of a circle, 2 pi r. Sorry, that's not 2 pi r. Pi r squared. Okay, good. Good, we're all here. Okay, so the area of a circle is pi r squared, and then we multiply by the height, h. Cool. Okay, good. Subject to the constraint. Here we use the 2 pi r. Plus 2 pi r squared. Yeah, 2 pi RH plus 2 pi r squared. So 2 pi RH is the area of the cylinder part, and 2 pi r squared is the area of the hemisphere part. So the reason is, if you're building this cylinder part, it's basically like you take a big rectangle of corrugated aluminum and you just bend it into a circle or a cylinder. And so if we pull this out, this part, the height of it is h, and then the distance, the width of it, is just the circumference of this circle, which is 2 pi r. Okay, so that is the area of this thing is 2 pi r h. And then for the hemisphere, you'd have to remember that the area of the sphere is 4 pi r squared. So if you didn't remember that, it's okay, but the area of a sphere is 4 pi r squared, so half of that is 2 pi r squared. And that is the total area, and it has to add up to 600 pi, because that's how much we have. Okay. So Lagrange multipliers equation says that gradient of f is equal to lambda times gradient of g. So let's write it down. So gradient of f, the derivative of this thing with respect to r is 2 pi r h. And the derivative of this thing with respect to h is pi r squared. And that's equal to lambda times the gradient of g. So the derivative of this thing with respect to r is 2 pi h plus 4 pi r. And the derivative of this thing with respect to h is 2 pi r. Okay. So that was the Lagrange multiplier step. Let's try to find the relationship between r and h. So writing this out, the first component gives us 2 pi RH equals lambda times 2 pi h plus 4 pi r. And the second component gives us pi r squared equals lambda times 2 pi r. Okay? Gosh, there are a lot of pi's. If I keep them all in, I will probably make a mistake. So I'll cancel 2 pi's in the first one. This was a 4 pi, so we're left with 2. And I'll cancel the pi's in the second one. So a simplified version that's equivalent is just RH equals lambda times h plus 2r, and r squared equals lambda times 2r. Okay, so my goal is to get a relationship between r and h. I don't care what lambda is. So it would be ideal if I could eliminate lambda somehow. You just have two equations and 3 variables, so you have to solve them somehow. There's not an obvious way of doing it. But one way would be to eliminate lambda. So from this equation, I could solve for lambda. Lambda is r squared over 2r. You have to be very careful when you divide by things, because things can be 0. So we should think, is it possible that r is 0 at a maximum? No, right? Because if r is 0, then our silo has 0 radius, so it has 0 volume. So it can't possibly be 0. So r is not 0 at a maximum. So it's OK to divide by it. So lambda is r over 2. Now we can put that into our first equation. So we have RH equals lambda, which we now know is r over 2, times h plus 2r. So we just put this equation down there and substituted this in there. Fractions are hard. Let's multiply through by 2. So 2RH equals r times h plus 2r. Let's multiply out the right-hand side. 2RH equals RH plus 2r squared. So we have RH equals 2r squared. Again, we know that r isn't 0 at a max, so we can divide both sides by r. And we get h equals 2r. OK. So this tells us that no matter how big you're making a silo, the volume maximizing proportions are when h equals 2r. So if you went down to your tiny family farmer down the street, and they were trying to make a tiny silo, you'd want h to be 2r. If you're going to the industrial factory farm, and they were trying to make an enormous silo, you'd want h to be 2r. It would be nice to know what this means. OK, h is 2r. So if we have r here, 2r looks like that. And then here's h. So here's h, and here's 2r. So it means that from the side, a maximizing silo looks like a square. So if you want to make the best silo, you make it a square. Have you ever seen a silo? Yeah? Does it look like this? No, right? Silos are tall and skinny. They look pretty much like the one I drew at the beginning. So this is why I got obsessed with silos last year, because I was like, why don't they make silos in the minimizing proportions? This is the best. Someone should have done Lagrange multipliers sometime in the last 300, 400 years. Why don't they do this? So I got really excited about it. I posted it on Facebook about why. People gave me all these answers. Do you have any ideas? Yeah.
Does it have to do with material properties and like keeping temperature the same and like other controls like that?
Yeah, material properties keeping the temperature the same. Yeah, it's something like that. So silage is not just like storing a bunch of dry grain. You're taking this sort of wet stuff and you want it to ferment. And you want to serve the cattle fermented stuff. And it turns out in order to ferment, you have to have pressure. So if you make your thing tall and thin, the stuff at the bottom, there's a lot of weight compressing on it. And so it has higher pressure. And so it ferments better. Also, if you've ever made sauerkraut, you may have. Sometimes people have a big vat of sauerkraut like in their garage, and it's fermenting. And the stuff on the top rots because it's exposed to oxygen. But the other stuff is not exposed to oxygen, so it's OK. So you would also want to minimize just the amount of area on the top that's exposed to oxygen because it rots. Yeah. I asked my mom about this because she grew up on a farm. So her family was farmers. That was their job. That was what they did. And I asked her why she thought that silos were tall and thin, even though it wasn't the maximizing proportions. And she told me this story about how her dad would have to go into the silo and spray this really toxic chemical around the sides of the inside. And it was so toxic that you couldn't breathe while you were using it because you would die. So he would have to climb up the ladder to the top of the silo, take a really deep breath, go in, and spray this thing around the inside. So clearly you wouldn't want it to be a very big circumference. So there's another reason. Okay.
What's the toxin for?
The toxin, probably to kill bacteria or bugs or I don't know. Good question. I didn't ask about that. Yeah. Okay, so now that we know that h equals 2r, this is the Lagrange multipliers relation between the things, and then we plug into the constraint, which was some crazy constraint. Our constraint was 2 pi r h plus 2 pi r squared equals 600 pi. So again, there are so many pi's here, I will probably make an error. So let's cross out all the pi's. And then we also have 2's, so this can turn into 300. Okay, so our constraint is really that RH plus R squared equals 300. That's so much easier to look at. And we know that H equals 2R. So every time we see an H, we'll put in a 2R. So R times 2R plus R squared equals 300. So 2R squared plus R squared is 300. So 3R squared is 300. So R squared is 100. Take the square root of both sides. R is plus or minus 10, but it's a radius, so it's 10. And now H is 2R, so H is 20. So for our particular farm, the best thing to do is R equals 10, H equals 20, except for what we've just discussed about silos. So for your homework, I'm going to ask you to do the same kind of calculation for an aluminum can, a cylindrical aluminum can. See if it's in the minimizing proportions. If it is, great. If it's not, discuss why you might think that it's not, that they made it not that way. Yeah. Okay. So now I'll tell you a story about something that happened last year. So I was going to put this question on a test. I thought it was a great question. And I thought, of course, you'd want to maximize the volume of the whole thing, the cylinder and the hemispherical top. So I wrote this question, and then I tested my exam by solving it. And I got a really weird answer. And I checked it, and it wasn't wrong. And I couldn't figure out why. So let's try to do that. So suppose we wish to maximize the entire volume, including the hemisphere. Because now we're allowed to put grain in the top too, under the same constraint. So then we would have F. So F of R comma H is pi r squared H. That's the volume of the cylinder part, plus half of a sphere. So the volume of a sphere is 4/3 pi r cubed. So half of that is 2/3 pi r cubed. Under constraint, G of RH is the same as before. Oh, I missed this. Sorry. Okay, G of RH is the same as before, 2 pi r h plus 2 pi r squared equals 600 pi. So if you write this down, gradient of f equals lambda times gradient of g, and you solve it, we would do basically all the same things, including the step where we solve for lambda as r over 2, assuming r is not 0. And if you solve this out, instead of getting h equals 2r, which is a lovely answer, we get r times h equals 0. Weird, right? Super weird. So when I saw this, I was like, oh, of course I've made an algebra error, because I make all the algebra errors. In writing out these notes for today, I made like 3 or 4 algebra errors. It's so frustrating. So of course, I figured I had made an algebra error. So I checked again. I hadn't made an error. I plugged the thing into the computer to see the level curves. They were indeed tangent here. They were not tangent anywhere else. I was like, what is going on? OK, so if RH equals 0, we already said R can't be 0 at a minimizer. So since R is not 0, this tells you H has to be 0. H has to be 0? It's very confusing. But let's think about it. So the one that we got before was that H had to be 2R. So if H equals 2R, then it looks something like this. It looks like a square from the side. On the other hand, if H is more than 2R, which is how it is in real life, then you get like a nice tall silo like this. And if H equals 0, you just get a hemisphere. Yeah, exactly. Which actually makes sense, because a sphere is more efficient at enclosing volume than a cylinder. So it actually makes sense. So it's just like bubbles. So bubbles, it's just like a bubble. It's what? Maximizing volume under a given surface area. Actually, bubbles are actually minimizing area given the volume that they're supposed to enclose. So if I had a soapy table here, if this table was all soapy and I made a soap bubble on it, it would be a hemisphere, because it's a given amount of air that the bubble has to enclose, and it's trying to minimize the amount of surface area. And that's exactly what this erstwhile silo is doing. Yeah. So if you just wanted to store grain and it wasn't fermenting or anything like that, and you had maybe your siding stuff is really expensive, you would want to make it a hemisphere. Pretty neat. Of course, there are other considerations, like it's probably easier to build rectangles. There you go. Yeah.
Are Lagrange multipliers only good for functions that have one maximum and one minimum, or can we use them for functions that have multiple maxima and minima?
Yeah, Lagrange multipliers will pick out all the maxima and minima. So the functions that we have discussed here today have only had one maximum or minimum, but they have multiple. For example, in the blob that you drew the last time, it might have had multiple equal maxima and minima. Yeah. They'll pick them all out. Yeah. Good question. Okay. Okay. So now that we have a way to feed our animals, we should probably also prevent them from running away or getting hurt. So let's make a pen for them. So suppose you have like a long fence or a side of a building, and you want to enclose some animals in a rectangular area here. So one thing that I could do is I could say, as before, I have a certain amount of fence, and I want you to maximize the area for my animals. So given the length, you can maximize area. That's what we just did, essentially. We were given a surface area, and we maximized the volume. I could also say, given an area that I want to enclose, minimize the length of fence. And generally, these will have the same answer, because it's just the Lagrange multipliers equation says gradient of f equals lambda times gradient of g. It's just switching the role of f and g. So unless lambda is 0, you get the same answers. So since we already did this one, I'm going to do this one. So I'm going to tell you it has a given area. It has to enclose 32 square meters. And I want to find the proportions x and y that minimize the total amount of fence that I'm going to have to put up. So I want to minimize f of x and y, which is the total length, 2x plus y, under the constraint that the area, which is just x times y, has to be 32. Okay, so let's do it. So Lagrange multipliers say lambda times of f, gradient of f equals lambda times gradient of g. The gradient of f is 2, 1. The gradient of g is y, x. So this tells us that 2 equals lambda times y, and 1 equals lambda times x. And we want to find a relationship between x and y. So there are lots of things you could do. If you could multiply the second equation by 2. Now both of these things are equal to 2. So then you'd have like lambda y equals 2 lambda x. But you'd have then one equation and 3 variables in it. So that would be sort of bad. But that would be an okay thing to try, but that wouldn't work. So maybe the thing to do is try to eliminate lambda. We want to get rid of lambda because we don't care what it is. So try to make the lambda sides look the same. So if I multiply the first equation by x, and I multiply the second equation by y, then the right-hand sides are equal. Yeah, lambda xy equals lambda yx. So since the right-hand sides are equal, I get 2x equals y. So this tells you that any time you have a free boundary, like this free wall here, and you want to make a rectangular enclosure in it, y should be twice as big as x. Which kind of makes sense because you're making it longer in this direction to take advantage of the free wall there. So our constraint, so this is our relationship that we got from Lagrange multipliers, and then we plug into our constraint. Our constraint was that xy has to be 32. Got to have 32 square meters for our animals. So x times y, which is 2x, is 32. 2x squared is 32. So x squared is 16. So x is 4. And y is twice as big, so y is 8. So x is 4, and y is 8. And again, you can check that this is a max by trying a nearby point. Yeah, all right, great, thanks.